of 2 to the power x. Okay, this is the function that you might have seen before, you haven't done before. It all doesn't matter. Okay, we just do it as as our first example. Okay, could everybody mute? Mute you. Okay. All right. Okay, mute. Do you hear me?
Yes.
Okay, good. Thank you, Farouz.
You're welcome.
Okay, guys, welcome back. We were doing the graph yesterday, didn't we? Did you guys continue to plot the points? Okay, that's what I want you guys to do. So when we graph, right, we want to mark the points. We want to mark the points. So for example, I'm going to show you how to mark the points, okay? When I use this software, it's not always super convenient to mark it perfectly, But ideally, when you do any graph, you always mark some points, okay? For example, in this picture, I will mark a few points. So this is how I mark the point, okay? The first one, I'm just going to show you some examples. The first one, the input is 3, the output is 8. But on this graph, there's a couple of critical points you absolutely want to mark. For example, this point, the y-intercept, you want to mark 0, 1. And the next one you want to mark maybe 2, 4. Input is 2, output is 4. Okay, and another point you may want to mark, I would mark this point. This point is input -1, output half. It would be best if you mark all of them, if you mark all of the points. Sometimes you make it too crowded, but the purpose of marking it is to tell the reader about, you know about this graph, tell the teacher. Okay, so in the future, if I ask you to do anything of graph, I will tell you how many points I expect you to mark. Okay, but it's always a good habit to mark some of the points, But anyway, without further ado, we have connected the dots, right? So in the process, we graph. In the process of graphing, we notice something very interesting, right? We notice something that no matter what is the input, the output are always positive. And in particular, as the input is getting larger and larger, the output is getting larger and larger from the table, right? So how is that reflected? How is that reflected on the picture, right? The reason we want to have a graph is because we want to see the visual, right? Yesterday, I emphasized the meaning of input. So today I promised you I was gonna type it, but I didn't type it, right? The input is the horizontal measurement from the origin. Okay, and the output is the vertical measurement from the same place. Okay, we talk about the input, we understand the input, but how about the output? So for each one of these points, you see the picture, you see the visual, it tells us a lot. For example, for the input of -2, the output is this high. Can you see that? Can you see that height? Barely, right? So let me make it just a little thicker, okay? This is how high the output. For input and -1, the output is half. For input 0, the output is what? Is 1. For input half, the output is the square root of 2. For input 1, the output is 2, and so on and so forth. Do you guys see that? So visually or mentally, you're drawing this horizontal line, and you see that the dots on the graph is getting higher and higher, which is reminding us of the definition of increasing function, isn't it? What is the definition of increasing function? For any x1, for any input x1 less than input x2, f of x1, the height, right, is less than f of x2. Are you guys with me? So we start to concisely see the picture as it should be seen in mathematics. And all of these bars, if you keep going in this positive direction, right? In this direction, the input is getting larger and larger. And we can imagine the green bars is going to get higher and higher, right? How about in the other direction? How about in the other direction? Let me remove that. It gave me the wrong thing. So here, how about the other direction? Right? How about the other direction? You can see the graph is kind of limited on what can be shown. Okay, so I want you guys to put on your thinking cap, right? We understand the tendency. In your calculus class, you're going to be verbalizing these tendencies. For example, here, you're going to say, as the input, right, approaches, as your input approaches infinity, the output, okay, the green bar is getting higher and higher. 2 to the power x is approaching infinity as well. So I'm going to put these little, the power right here. Okay, I will rewrite this, okay? So as x approaching positive infinity, 2 to the power x is approaching positive infinity. And they're always positive on this side. How about on the lower side? Did you guys write it down? Because I'm going to erase. Okay, I'm going to observe this side. I want you to have a feeling of it. Okay, I want you to have a feeling of it, a feel of it, whatever the right word. Okay, now, anybody said anything on the chat? No. Okay. This part we're doing is actually called analytical geometry. Analytical geometry. A lot of our student, when I taught them in calculus class, what I found that these students just need a little bit more training in analytical geometry. But doing analytical geometry, and that's what we're doing. What we are doing, we're doing analytical geometry. Okay, you guys know geometry, right? Geometry, you draw triangles, lines, rectangle, squares, or whatever, trapezoid. Analytical geometry basically is bring the picture to a rectangular system. That's analytical geometry. So analytical, the word analytical is like a digitized. It's a digitized geometry. Why is it digitized geometry? Because we put a concrete measurement in that process. Does that make sense, you guys? So what we're doing here is analytical geometry. We're doing something really, really helpful, and it's very useful for your future classes. Okay, so with that said and done, assume you have written them down. I'm going to clean this because I'm going to want you guys to observe this corner. Okay, I want you guys to observe this corner, and I'm going to clean this up. Okay, so let's observe this corner. To observe this corner, we basically will see, we want to see what happens, right? We want to see can't stop that. It's some kind of alert. Okay. All right. We want to see this. When the input approaches negative infinity, what's going to happen? This can only be seen in our mind's eyes. Why is that? For example, the computer graphing will not be able to generate that picture for us. Okay, will not be able to generate that picture for us. But what do we see here from the pattern, right? As x approaching negative infinity, what happens is that the input is a horizontal measurement from the origin, right? So the input is getting away and away from the origin to the left. And those numbers, right? You see from -1, -2, -3, and you can imagine -3, -4, -5, -6, and so on and so forth, -10,000, -20,000, and so on and so forth. And the curve and these dots is getting lower and lower and lower, but never touch the x-axis. Can you imagine that? Can we imagine that? So I'm going to show you a number, okay? So I'm going to show you a number to see the concrete thing. What I'm going to do is I'm going to take an example. Okay, I'm inserting a row here, okay, and the position here. Okay, I'm going to put the input as -100 because that's going to help my imagination, right? Putting as -100. According to the rule of the function, it's going to be 2 to the power. The output is going to be 2 to the power -100. And what is 2 to the power -100? We talked about how to handle these yesterday, right? Can you guys tell me? What will be the other form of it? Anybody? That's 2 to the power of 100 under 1. Right? Do you guys see that? Yes?
Mm-hmm.
All right.
Yes.
So how big is this number? Definitively, it is not a 0. Definitively, it is larger than 0, isn't it? Right?
Yes.
It's going to be a very small positive number, i.e. that red dot, if we are to draw it, it's going to be very, very close to x-axis, but does not touch x-axis. That's the image you see. So in this direction, as x approaching -infinity, the red dot is going to keep going down, 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 but will never touch the x-axis, and it will get infinitely close to x-axis. Do you guys follow me? And I have to say, the graph I'm doing cannot show you that. You have to imagine that in your mind. That's part of calculus. That's part of calculus. You will need these little bits and pieces putting together to set your imagination on some wings. Okay, so even though this number is never 0, getting as close to 0 as you want, because you can keep choosing the input to be -101, -105, -10,000, and so on and so forth. These numbers will keep getting smaller and smaller, but never get to be 0. With all these said, what I'm trying to say, I'm describing a situation is that when x is approaching -infinity, 2 to the power of x is going to be positive forever, and yet 2 to the power x is going to approach 0 as low as possible, but never touched it. Never touched it. Is everybody with me? All right. So this is going to bring out, what do we say about the range? what will be the range for this function? With the picture we have seen here, what will be the range? And we know those vertical green bars, those are, you know, the outputs. So what would you tell me about the range of 2 to the power x? Anybody want to volunteer an answer?
I would be the last.
I know. Could I call on someone? Jacob?
I would want to say it would be negative infinity to positive infinity because it never actually gets to 0, and it can also go as far as it wants to any other side.
Okay. We got some responses, and I really appreciate that. Actually, Jacob says from negative infinity to positive infinity. Right, and there's another response on the chat. It's Wilbur's x, and this is less than infinity, and 2 to the power of x is greater than 0. 2 to the power x is greater than 0. Okay. So I'm so glad you guys are responding, right? First of all, negative infinity to positive infinity, this is telling us, okay, so first let's try to understand what this is telling us. This is telling us 2 to the power x may be 0, maybe negative, okay? In the graph, from negative infinity to positive infinity, meaning that those green bars could be underneath the x-axis. You follow me? What's the meaning of that? That's what it means. Okay, remember the green bars I was drawing for you? Right? All these green bars, those are the range. All of these are in the range. And many green bars that could be on this side. And all of these green bars are in the range. If you tell me that it could be from negative infinity to positive infinity, you are telling me that there might be some green bars underneath. Would that still be your answer?
No, I see where I did wrong now.
So how would you correct it, Jacob?
I would say 0 with a bracket and then to positive infinity.
Okay, so we have a change of mind, and 0 with a bracket. Thank you for that specifics. So 0 to positive infinity. Now the question is, you're telling me, okay, this is what you're telling the reader. You're telling the reader 2 to the power x can be 0. That's what you're telling the reader. Do you agree with that statement? This is you're telling the reader, right? 2 to the power x can be 0. Oops. What's going on here? 2 to the power x can be 0. This is what you're telling the reader. And a positive. That's what you're telling the reader. Would you still agree with that statement?
No, it's wrong.
And then what? How would you correct it? You're so close, so close. It can never be 0, right? We just talked about the output will never be 0. It will always be a little bit larger than 0, but it gets infinitely close to 0 from above 0. You follow me? In fact, if I use a proper mathematical calculus notation, you will write it like that. 0 is a plus sign on the shoulder, which means that the dot is coming down to x-axis, infinitely close to it, but never touched it. Never touched it, meaning the output will never be 0. Okay, therefore, the correction you would like to make would be that. Okay, so this is the first option, right? You can see we can totally go back and forth and analyze it and check our answer, double check our answer, and so on and so forth in order to reach the right conclusion. So that's the correct answer. The second one, these two mean the same thing, okay? But the x is in the wrong place because x is the input. Do you remember? X is the input. So we should have written as 2 to the power of x is larger than 0, less between 0 and infinity. Well, by the way, infinity is a number that does not exist. Even though we use that symbol, infinity is a number that does not exist. It just tells us that number can be as large as possible. So this notation, okay, see, if you put x there, it's wrong because the x represents input. We are discussing output. Range is about output. Therefore, this x will need to be replaced by 2 to the power x. You guys follow me? And the last statement, 2 to the power x is larger than 0, is the correct answer. All three are correct. So which one is the preferred? Very good job, you guys. Okay, I hope that through these discussions, you'll be able to, make a lot of judgment calls on yourself, okay, by yourself. This is the preferred form, okay? This is the preferred form. This is okay, but it's rarely used. We usually just use this one. And this one is sometimes used in a lot of literatures, and I believe many of you probably would use this, but whenever you use this one, I'm not going to give you credit. I will acknowledge its correctness, but I will not give you credit. And 2 to the power x larger than 0 will be the one that will earn you the credit. Remember, I told you I want to train you guys to use inequalities properly. Now, domain and range are both done. We have a one sentence domain range. Okay, so we have a domain range in one sentence combined. What do we say? And this is what we say. I want you guys to write it down on a flashcard if you wish. 2 to the power x is larger than 0 for any real number x. You see how this sentence has been written down? The domain is any real number. The range is always positive. If I put them together, I get this sentence. So please write it down. Very, very useful statement. Very, very useful statement. Okay. So far, so good? Even though 2 to the power x is a very, very good function, very interesting function, right? It's very easy to plot. Unfortunately, you're not going to use it very much in calculus. You probably use it very rarely. So which one of these exponential functions? I give you 3 in basic 1. Okay, 2 to the power x, e to the power x, 10 to the power x. The one you're going to use all the time is e to the power x. Okay, so next, I'm going to work with you to plot e to the power x. Okay, e to the power x. For e to the power x, everything stay almost the same. The only difference, okay, the only difference would be the change of base. Okay, I basically assume none of you have done this before, because typically in your previous experience, the teachers were teaching this. They would just say, oh, we do the 2 to the power x because it's easy to do and the number is easy to grasp, right? And e to the power x is similar. And you're supposed to do it. And the result is that no student will do it because the teacher didn't do it in class. Am I right? Which is understandable, totally understandable. But I would do something different from your previous experience. I'm actually going to do it with you. I'm going to do it with you. Okay? Now, are you ready? This is this one single function that you're going to use many, many times over in your calculus classes. Even in, what do we say? Differential equation, linear algebra, you're going to use this function. And you're going to use this function in its various forms. Would it be necessary for us to know it's a very basic form? Absolutely, absolutely. Okay, so let's roll up our sleeve. Let's do it. Okay. Paper, pencil, please. Please get your paper, pencil. We must crack this code. Okay, as a matter of fact, I'm going to introduce this function notation still. Yesterday I forgot to use this, but it's never too late. Okay, so what are the things we're going to examine? Oh, by the way, I forgot to do the intercept for 2 to the power x. So let's get it quickly done. Okay, let's get it quickly done. What are the intercepts? The x-intercept and y-intercept for this function. Huh? What is the x-intercept, y-intercept for it? For 2 to the power x, by the way. Andre says 0, 1. What intercept would that be for? X? Okay, so you tell me the x-intercept. That's, yeah, do you guys see the discussion? No, don't apologize. I totally appreciate these discussions, because by these discussions, everything is made completely clear, completely clear. Wonderful. So both of them answer the question, and the right answer is the y-intercept is 0, 1. X-intercept, no x-intercept, none. Perfect answer. Okay, perfect answer. And the picture tells us so. Because what is x-intercept, right? So let's read the word, think about the meaning, and think about the most possible meaning, right? You can see we just talked about the curve will never touch x-axis. There's no crossing. There's no crossing. Therefore, the crossing doesn't exist. So x-intercept means the curve, the point where the curve crosses the x-axis. Since this curve never crosses x-axis, so we have none, right? And y-intercept means what? It's where the curve crosses the y-axis, which is the output axis. And we got one, 0, 1. 0, 1. Therefore, the answer is right. Congratulations, you guys. Okay, very good. So these are the two things we missed. And let's go back to e to the power x. For e to the power x, I want every single one of you do it with me. Okay? The only person that doesn't need to do this in this classroom is me and Farouz. Every one of you need to do this. Okay? But we're going to hold your hand. We're going to do it with you. Okay? Now, first of all, we see that the difference between y equals 2 to the power x or e to the power x, the only difference is it's just the base, right? E. What is E? Could anybody tell me what is E? Why E to the power x is so important? Why couldn't it be 3, 4, 5? It turned out this number is very useful, very, very useful, not only in mathematics, also in finance. Okay, in the calculation of compound interest and so on and so forth. Okay, if we have time in the future, I will give you a glimpse of it. But in calculus 1, you will definitely touch that form. You will definitely touch that form. Okay. Now, E is just a number. Okay. There's a book written about E. Okay. I used to have it on my shelf. Okay. And I don't want to work too hard to find it. Once I find it, I will show you in the classroom. Okay. E. I'm going to bring back the numerical value of E. And this one shows only 4 decimal places after decimal point. Actually, there are many, many, many decimal points. Many, many decimal points. As many as you wish. And this is a very interesting number. And this number turned out to be very, very useful. Okay, but all we need to know is that we know that E is between 2 and 3. Between 2 and 3. You don't have to worry too much about this number. For that reason, a lot of teachers who have worked with in your previous experience, right? A lot of the teachers, what they did is that they did a 2 to the power x, and maybe they would do 3 to the power x. Okay, 3 to the power x. I'm not going to do 3 to the power x in the class because that's going to take an awful lot of time. So 2 to the power x, 3 to the power x. And then, and they will tell you e to the power x is very similar to them, and e is a number between 2 and 3. Okay, so that's a typical story. That's a typical story. Now, when you're heading to calculus class, you can no longer avoiding e, so we're gonna attack this one thoroughly. So e is a number between 2 and 3. The reason we use e is because it's so much more easier. You don't want to type a base of a number like this, don't you? Right? You don't want to. So we just use E to represent it. As a matter of fact, the symbol E, if you look through the mathematical textbooks, this number is so important. This notation E is reserved for it, like I, right? You're not going to see another E. Every time E is mentioned, it's addressing this number. This number has, infinite number of digits. Okay, you can just keep going forever. So now I hope that gave you enough introduction about E. So treat E as a number between 2 and 3. So what do we want to study? We want to study, of course, we study domain, range, and graph. Domain, range, graph. Okay, so what will be the domain? Some of the questions we may not be able to answer right away, but it's okay. Okay, we'll come back to it. But to answer these questions, we often start from the place which is the simplest to handle, easiest to handle. And I have a sneeze coming up. Sorry. Graph. So we usually start from the same place, the graph, plotting the points. Okay, so what I'm going to do is I'm going to copy the same graph, the same table we made. So you see the similarity. So this time you truly see the similarity. But I'm going to do some operations with you. Okay, I'm going to do some operations with you. So I copy and paste, but this time the function is different, right? I'm going to maintain the input, And the output will be different because we are handling a different rule. Could you guys do that along with me? Do you guys follow me? The output is f of x equals to e to the power x. Okay, so here this is going to be e. Okay, this is going to be e, and that's going to be e squared. 1 over e squared. So this is going to be e. This is going to be e, 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 e squared. Sorry. E to the power 3. Okay. So in terms of using notation, we're just going to put these here. I want you guys to take this opportunity to practice with your notation. Okay, I'll give you time. Do you guys have, anybody has any questions? Input, output? Input a -1, input 0. You get to use these notations over and over again. And very soon you'll be the master of it. That's all it takes. That's all it takes. Practice makes perfect. Easy to do and easy not to do. Okay, so let me make this just a little bit manageable. Okay, so this input is going to be -100 and 1 over e to the power 100. Okay, and over here, the output is 1 over e to the power 3. You can use any one of these numbers, really. You can use this guy. You can also use this guy. They're the same number. They're the same number. And over here, you can use 1 over e squared. And over here is 1 over e, or you can use e to the power -1. You can use either one because they're the same, right? And this is just 0, 1. And over here is going to be square root of e. And this is e. And this is e squared. And this is e to the power 3. Does everybody follow me? Does everybody understand how this table is made? Any question, please? If you don't feel comfortable to ask questions in front of everyone, please private message me. Private message me, okay? I'd appreciate it. I don't want anybody to be left behind. So that's E.
So I understand what you're doing here with the table, just with the input output, like just from left to right, but I joined a bit late, so I'm kind of just like behind on where we're at overall right now.
Okay, so what we are at, right? Do you remember what we did yesterday?
Oh, we were doing increase.
We did a 2 to the power x, right?
Yeah.
So this was a 2 to the power x. 2 to the power x. For 2 to the power x, we have chosen the input -100, -3, -2, and so on and so forth, and we produce the output, right? We produce the output. And we made this table, input, output, input, output. Did you get that?
Yeah, I see that, yeah.
And what we were just doing then now is that we replace the base by E. Because we're handling e to the power x.
Okay.
So for e to the power x, you can see there's a slight change of rule. Okay, there's a slight change of rule. The slight change of rule is basically, it was x, right? And the rule is going, instead of being 2 to the power x, right? Instead of being 2 to the power x, we did it yesterday. And we change the base to e. And what is e? E is a number between 2 and 3. It's an amazing number. You're going to study this e. You will continue to study e in calculus. And here, we're just getting the basic of it. Okay, so e is a number between 2 and 3 because e is such a messy number and yet it is so important. We decide to dedicate a symbol to it, and that symbol is called e. So when you think of e, you think of e as just a number, and that number is between 2 and 3. In particular, it's about 2.7. So with that, we're dealing with plotting the points, and we want to be able to identify domain range intercepts on the graph, of course. Because we may not be able to identify all of these all at once. And we start from the very basic movement. We just plug in some numbers. So does that bring you with us?
Yeah.
Okay. Okay. Now, when my input is -100, okay, so I'm leaving this line here for some future use. Mainly for input -3, the input is -3, the output will be e to the power -3. E to the power -3 is 1 over e to the power 3. That's 1 over e. So I can totally just simplify this piece, right? When input is -2, the output is e to the power -2, because that's the rule. So 1 over e squared. I use the positive exponents form, but you can totally use these forms. No problem at all. No problem at all, because they're all the same number, right? Anybody has any questions about these operations? We did those yesterday. We reviewed the powers and stuff, right? We give you homework, which is basic 33. And we give you, homework basic 21 for you to review this part. And if you have any questions, so please don't hesitate. And for e to the power half, we get square root of e. For e to the power 1, we get e. For e to the power 2, we get e squared. For e to the power 3, we get e to the power 3. So we got all of these points. Does everybody follow me?
Yeah.
Okay, so now let's go back to see domain range. It looks like the domain, we can use negative number, fraction, positive number 0 as the input and produces meaningful output. For each input, there's exactly one output. Am I reciting the definition of function? Am I reciting the definition of function?
I didn't really hear the question. I'm sorry. Could you repeat that?
Okay. Can you pull out the definition of function? Pull out the definition function card. Okay. When I look at this table, for each input, there's a unique output. For each input, there's a unique output. And what are the numbers will be qualified for input? Because we're thinking about domain, right? What are all the possible numbers that are qualified for input?
All real numbers. All
That's
real
right.
numbers.
That's right. So these observations, these basic observations help us to, from some anecdotes and generalize, and then draw our conclusion. You see that this is a typical method in mathematics, right? Of course, as a lot of times we use that all the time. So the domain is from -infinity to positive infinity, i.e. your input can be positive, -0, positive, -0, right? 3 kinds. And any real number, any fraction, decimal, and so on and so forth, right? And let's look at the output. The range is about output. All right, some of you might already have the answer. I know. Just hold it. Hold it. Okay. Intercepts. Okay. Intercepts. X-intercept. Y-intercept. Okay. But before we do that, I want to plot the points. I want you guys to plot the points with me. Okay. We're so close to get a picture. Why not? Let's get a picture. I want you guys to plot the point with me, please. I kind of want you guys to remember me by doing all of these with you guys. Okay. Because I know this is going to help you so much. Okay, so I've set up the rectangular system. I need to make some more adjustment. Here. There. Okay, so we're going to plot 1 point at a time. This one, I'm going to wait. Okay, I'm going to start with this guy. Okay, then you say, hey, how am I going to do 1 over e to the power 3? Okay, that's a good question. So what I'm going to do is I'm going to start from the bottom, right? You can see we have all these flexibilities, right? We have all these flexibilities. Then you say, oh, what is the value of e to the power 3? How am I going to plot it? I'm not asking you to do it precisely. I'm asking you to estimate. I'm asking you to estimate. For example, right? I'm going to start with 3, e to the power 3. Input 3, output e to the power positive 3. The second one is 2, e squared. Actually, I think this one will be much easier, isn't it? All right, so let's do it. Oh, by the way, maybe 1, e is even easier, isn't it? So what you do is you basically look at these points. Which one is the easiest to plot? Tell me, which one is the easiest to plot?
0, 1.
That's right. You are absolutely right. Why don't we start from there, right? All right. You can see there's not really a right place to start. You can start. So I'm going to plot this point first. Boom, a red dot, 0, 1. Yes, is that easy? I'm sure you're already doing it. So you can start from somewhere easy. That's what the math always do. We start from something easy and we build on it. Okay, so we did the easy point. Okay, and this point looks a little messy. So how about 1, e? Do you agree with me? 1, e will be the next one.
Yeah,
right?
I agree.
It might be easy for me to say because I'm using this software, right? It would just do it for me. But for you, what do? Just remember, e is a number between 2 and 3. It's approximately 2.7. So what you do is on your paper, right? What input is 1, output is 2 points, is e. You just approximately between 2 and 3. You pick a point between, closer to 3, then it's closer to 2. So you just put that dot. I'm not going to hold you accountable. Say, oh, you should be a little bit higher or a little bit lower. Just approximate. You guys follow me? It's actually a sketch. The relative position is more important. Yes? Does everybody follow me?
Yeah, yeah.
You see? Now, well, as you're doing this, I'm asking you to do one more thing for me. I'm asking you to do one more thing for me and make this a habit, okay? You're gonna mark these points, 0, 1. And this one, 1, E. Could you do that for me?
Yeah, simple.
When you're graphing e to the power x, you always mark that 0, 1. And your professor and your professors in the future will appreciate it. And she or he cannot help just to give you maybe a little extra point. I don't know, possibly. I'm just speaking from my perspective.
Maybe a smiley face.
That's right, a smiley face. Are you guys following me? So now, how about the rest of the points? How about the rest of the points? Okay, so let's do another one. Let's do another one. This one I'm going to do is -1 because I want to see some points for the negative input. I want to see the point for 0 input. I want to see some points for the positive input. Okay, this is a typical, what do? We just cover a little bit of every area and have assessment, right? So this point I'm going to do is going to be okay, right there. Right there, you see the points and what the places are kind of, you know, moved. So, but you guys know what I meant, right? There's a limitation that these two software don't really talk to each other. So I'm also going to mark this point, right? This is -1 and the comma e to the power -1. You can use either one. If you mark 3 points for e to the power x on your picture, it's pretty good. You don't have to mark more. You could mark more if it's, you know, make everything, if you can space them well enough, because sometimes our graph can be very crowded, right? And you just keep doing that. So and we keep plotting. Okay, so let's keep going. Okay, I'm gonna leave the rest of the points for you, except the the one on the top. And you don't have to mark them anymore. But if you want to, that's great. It's still wonderful, right? So I'm going to put all of these points in place. Okay, mark this point in place and add another point, right? This is going to be -3 and e to the power 3. And I'm adding more points, which is that half and root of e, right? And one more. This is going to be positive 2e squared. Right, one more point. +3 e to the power 3. Boom. So I just put all the points in place, and I must have done something wrong, didn't I? How did they get there? No problem. Everybody makes mistakes, including me. Right, -1, -2, -3. Half is right. That's the problem. E squared. See? We can identify these mistakes. That's e to the power 3. That's what's wrong. And there. All the points we plotted but one. Okay, the one on the top. Okay, I'm not going to do that right now. You can see the limitation, right? You can see the limitation. This dot on -3 is on x-axis. That's not right. This software is not doing the job. Or we can say we didn't choose the scale properly enough. Okay, so now I'm going to remove all these markings, but you know you need to mark some points, right? So this point is misplaced, I have to say. It should not give us the impression that the curve crosses x-axis. It never does. Okay, it never does. But anyway, last but not least, I'm going to connect the dots. I'm connecting the dots. Connecting the dots. Okay, so in this case, you cannot totally rely on the picture, because the computer software, no matter how sophisticated, it just cannot represent infinity. And sometimes what it can represent is very limited in certain area, because the limitation of computing is finite. So we have to be able to put on our thinking cap, right? So even though this point is like, gee, it's so close, right? I'm gonna make this to see if I can make some space for you. Right? Do you guys start to see the space? You see this dot, this lowest red dot is actually above x-axis, right? It should not give us the impression that it is on x-axis, therefore the curve crosses x-axis. No, that's entirely wrong. Because from our observation, this is a positive. And this is a positive. So all of these dots and the dot we didn't plot, the one on the very top, is going to be above x-axis, but closer to x-axis. Do you follow me?
Yeah.
So as a result, we see a similar picture to 2 to the power x, don't we? So these dots, okay, as x approaching negative infinity, these red dots is going to getting lower and lower and lower and lower and lower, but always above x-axis, getting lower and lower and lower and lower. Do you hear me? Infinitely. Never touch x-axis. Do you follow me?
Mm-hmm.
On the other side, what happens? On the other side, what happens? So if you look at those green bars, right, those are the outputs, right? Those outputs, right? The outputs are vertical measurement from the origin. So as our input getting larger and larger in the horizontal direction, our output is getting higher and higher yet. On the other direction, as x approaching negative infinity, those red dots, those green heights, the green bars are going to getting shorter and shorter and shorter and shorter, never becomes zero, always larger than zero. Does that sound familiar? Am I too slow?
Well, what was the question? I was writing something down. I'm sorry.
Okay, so those are green bars, which represent the output, right?
Yeah.
And they're sitting on those red dots, and my input is getting to negative infinity, right? In this direction. Okay, hold on. So my input is getting in this direction, getting smaller and smaller and smaller. What happened to the red dots? To getting lower and lower and lower, but never as low as zero, because it always larger than zero, but never touch zero. Isn't that the same description we had for 2 to the power x?
2 to the power of x. Yeah, I believe so.
Right. So let's summarize. Let's see how we express these observations mathematically. Okay, so I'm going to clean this up. Okay, so on the graph, you guys have the graph in front of you, right? As x approaching infinity, positive infinity, 2 to the power x is approaching infinity. Yes? As x approaching negative infinity, this is essentially calculus notation, okay? These are essentially calculus notation, right, Farouz?
Yes, ma'am.
2 to the power x, 2 to the power squared, that's wrong. Approaching 0, but never will be 0, is going to be larger than 0. So that's the notation you will be using. And that's what it means. That's a description I just mentioned. Okay. The first line, meaning as the input gets larger and larger, the output is getting higher and higher. Okay. And when the input is getting smaller and smaller, the output is getting closer and closer to 0. Those red dots is getting lower and lower and lower and lower, as close to 0 as possible. So you can only see that picture in your mind. Do you agree? At least I cannot show you. With the tool I have, I cannot show you. Sorry.
No, I understand. It makes sense.
Very good. So I want you to understand these details, and also you can have a narrative of it. Okay. And this is the narrative, and this is the mathematical expression. This is the mathematical expression. So okay. So with that said and done, what is the range? What is the range? We should take a break in a little while, okay?
Wouldn't the range be like, since you can't go beneath 0, it would be like 0 to infinity?
That's right. From 0 to infinity. Very good. And Wilbur said e to the power x larger than 0. E to the power x is greater than 0. Perfect answer. You guys got the perfect answer. Maritza and Wilbur, wonderful, wonderful. That's it, right? And you also give me the preferred form, the form I love to see. Every time I see it, I smile, right? And this is the form is going to earn you points. Can we make that one sentence domain range? What is that one sentence domain range? Any real number. For any real number. Okay. All right.
Sounds like a flashcard material, Professor.
Thank you. Thank you for the reminder. Did you guys hear what Farouz is reminding us of?
I didn't really hear what you said. No.
Super useful. Okay. I will show you how this sentence will be used in the lessons to come. Now, what's the x-intercept? What's the y-intercept? Look at the picture again. What's the x-intercept? What's the y-intercept? Where the curve crosses x-axis, where the curve crosses the y-axis.
So y would be 1, 0 would be not a thing, or x would be not a thing.
X-intercept none. Wonderful. Y-intercept? Great job. Great job. Okay, so next I'm going to summarize with you for 2 to the power x and e to the power x. And then we take a break. How about that? Or you want to do that after we come back? Are you tired?
I'm not tired. I don't know. I
Okay,
don't
good.
sleep for
So let's
very long.
summarize. Okay, let's summarize. Summarize just these two pictures, right? Summary. 2 to the power x, e to the power x. I'm gonna make a little table. Okay, so the function is 2 to the power x, e to the power x, right? Let me put it over here. Oh, so bad. Here. Functions, our function notation. Okay, if you want to, right? These are the functions. And graph. This is 2 to the power x. Right? And that's the e to the power x. This is the so-called, your professors say, oh, they're similar. Yes, they are similar indeed. Okay, but they each have their little slight, little different things, okay? So now x-intercept, and I'm sorry, the rule, I still want to emphasize the rule, okay? Because I'm addressing function. Remember I mentioned this, the entire semester, the theme is function. Various different kinds of functions, okay? So I will never forget that. I'll never forget that, okay? That's the rule. And the output is 2 to the power x. So you always reflect on the definition of function. And the next rule, the only difference is the difference on the base. Plotted all these points, you can see how similar these two pictures are, right? But would you like to put these two pictures on the same graph? That's something I want you to think about on the break, but let's continue to summarize, okay? Domain, range, right? What's the domain for 2 to the power x? Negative infinity to positive infinity. And what's the range? 2 to the power x is larger than 0. How about the other one? How about that one sentence? That one sentence. Domain range. 2 to the power x is larger than 0. I'm going to use a little mathematical notation here for all x. So this is going to be e, and that's going to be that. Okay, intercepts. Okay, intercept. Okay, so I need one more row. X-intercept. Y-intercept. I'm gonna make the graph just a little bit smaller so you can see the whole of the picture, and that's where we're gonna pause. And I introduced this little notation here, okay? I want you guys to learn to use it. There's a lot of interesting shorthand notation. So this notation means for all. For all, just for all. Okay? So this little notation has a meaning of for all. I don't know who invented this notation, and you know, someone invented it, and I like to use it. Okay, because I don't want to make the table too spaced out. Okay, all right. How about that? Do you feel achieved?
Mm-hmm.
Good. I'm gonna give you guys 6 minutes break. 5 minutes, well, 6 minutes break. Come back at 9:20. How about that?
Sounds good.
Okay.
Thank you. Okay, so come back at 9:20. 9:20, and today's lecture is until 10:05. I hope you guys understand, right? It's a Thursday. So I will be back in you know, at 9:20. Okay, see you soon. Very good job. Okay, you have accomplished one of the, you know, very important function you are going to use a lot in Cal. Okay, so I'm going to leave the picture on the screen. I will see you soon.
Do you want us to put those two graphs into one coordinate system, Professor?
Correct.
So if we do that, then they have a same common y-intercept at 0,1. One of the points, comparison.
Very good. Very good. Okay, so if you look at these two pictures, right, because this picture, they're almost identical, but we understand they're not exactly the same. Okay, they're not the same in the details, right? For example, if I'm gonna do this for you guys. I know my questions kind of need more elaboration. So what I'm gonna do is I'm gonna put this input. I'm gonna put one table. I'm gonna put these two tables next to each other. Okay, that's what I want you to do as well. Okay, I'm going to put these two tables next to each other. The first table and the second table. The input are all the same, right? I give you guys all the same input. But for each output, right, you look at the output. For 0, 1, Farouz just pointed out, they have the same y-intercept. They do, right? Because one is 2 to the power 0, the other one is e to the power 0. They're equals to 1. So there's one point that will overlap, right? On the positive number sides, for the same input, do you guys see the same input? The output for base 2 is smaller than for the output for base E. That means that these points are going to be lower than these points. Do you follow me?
Uh-huh.
Agree?
Yeah.
Now, let's look at the other side. For the negative input, negative 1, 2, 3. Negative 1, 2, 3. For the same input, 1/8, okay, is actually larger than 1 over e to the power 3 because e is larger than 2. And it's in the denominator, therefore the 1 over that number is going to be smaller, right? So on the negative input size, e to the power x is lower than 2 to the power x. Okay, and the other thing I want you guys to do, the easy thing to do, okay, and then we're going to come back to it. We're going to come back to this observation. Okay, so what I'm going to do is I'm going to draw e to the power x. For me, it's easy, and you can do the same if you happen to have a graphing calculator. If you don't have a graphing calculator, that's not a big deal either. It's not a required. It's not required for you to have a graphing calculator for this class. Okay, so I'm going to just show you in front of your eyes. Okay, so this is the rectangular system I'm setting up within the range of the numbers we in our consideration, e to the power x, right? E to the power x. I'm using the black color. Okay, next, I'm going to plot 2 to the power x in the same picture. If you have a calculator, you can totally do this, right? I'm going to change the color. 2 to the power x is red. Do you follow me? So this is e to the power x. And that's 2 to the power x. And they have a, as we said earlier from the table, right? From the table, could you guys look at the table at the same time? On the positive input, e to the power x is higher than 2 to the power x. On the negative number input, 2 to the power x is higher than e to the power x. And they have a point of common points. And that common point, and the coordinate is 0, 1. 0, 1. I have a next question. Okay. If you are to plot 3 to the power x, can you sketch it without plotting any points based on what we have done? Could you plot? Could you sketch with relative position in mind? Just put on your thinking cap. There's no pressure whatsoever, right? Because this is kind of recollect your sense of numbers and about the base. And besides, this is actually very relevant in our current situation. We're in pandemics. The growth, the spread of the virus is exponential. Okay. The spread of a virus is exponential. But depending on the base, if it's base 2, it doesn't grow as fast as e to the power x. What if it's base 3? So where do you think 3 to the power x will be?
You could start with a 0, 1, just like the.
It's going to cross 0, 1 again, right? Very
Yeah.
good. And then what?
And then you can just do like 1, 3.
That's right. That's the right way to think, because you start to look at the points, you see the relative position. So the first point will be 1, 3. So that's going to be higher than both of them, right?
Yeah. Yeah.
Are you sure?
It looks a bit higher than the e to the power of x.
That's right.
I mean, it should be because it's you
On
know,
the
larger
positive
than-
side, on the
yeah, on
positive
the
side.
positive side, it's larger
On
than
the
3.5.
negative side will be lower than both of them.
Yeah.
Are you guys with me? Are you guys with me? I want you guys to think. Okay, I want you guys to think. Okay, and I'm going to give you some tools. I'm going to give you some tools. Okay. On the positive side, okay, we know that 2, hold on, I'm going to put it here. 2 is less than E is less than 3, right?
Yes.
So for,
Agreed.
I'm sorry?
No, I was just saying yes. I agree.
You agree, right? And as a result, remember, I want to train you guys to be better at inequality, right? I always try to keep my promise. For x is positive, these relationships still hold. So 2 to the power x, x to the power x. You follow me? For x is negative, these relationship will be reversed. Okay, you can try a couple of numbers. For example, you can try -1, right? You will see half is larger than 1 over E is larger than 1/3. Do you follow me? Yeah. Examples. So I'm going to give you examples. Okay. Example. Square. Example. Okay. Yeah. Sorry. Agree?
Agreed.
Everybody, please don't hesitate. These are not always very intuitive, not always very straightforward, but I guarantee they're going to be useful for you in your future classes. These are the devils in the details. These are the devils in the details, right? So now, with that said and done, okay, now you have sketched, right? Have you sketched 3 to the power x? I'm not coming to your house to check on you. Okay, it's just for your self-check, right? So what I'm going to do is I'm going to plot the 3 to the power x on this picture. So it may or may not confirm your sketch, but at least, you know, we see the picture, right? So I'm going to sketch 3 to the power, I'm going to graph 3 to the power x in green. Are you done the sketching? Let truth be to be revealed. You see, green is higher than both of them, lower than both of them on the other side. And it also crosses 0, 1. Do you follow me? The next one. So you can see if these are the curves to describe pandemics, the spread of virus, if the exponential function is base 2, it's better than base E, better than base 3. What if we have base 10? 10 to the power x is one of the functions in basic 1, right? What is base 10? Hello? Hello? Are you with me?
It's gonna be a steep graph.
Less than 10, yes, it's going to be a steep graph. Okay, and this inequality will continue for x is positive, and this is going to be continue. Okay, so this is going to be true, 10 squared, right? And these numbers just show up in your eye in front of you. Right? Are you ready to see the actual curve?
Yeah.
10 to the power x. What color do you want?
Something scary, like brown.
Brown. All right, brown. So let's do the brown. I think you got it right. Okay, I'm not coming to your house to check on you, but you got it right. So if the base is 10, the spread is going to be even faster. Okay, so we all know that, virus is exponential growth. But what the base makes a difference in how fast. How fast. Okay, in the positive number direction, you can see base 10 is the fastest among all 4. Right? But in the negative direction, it's not. 10 to the power x is it's the lowest. But anyway, so this is just for the fun of it. How do you get those curves? The same method. Okay, so I'm not going to do 3 to the power x, but you know how to do it, right? You're going to basically do the same thing with base 3. For 10, you're going to do the same thing with base 10. So your output will be different, but for the same input, you plot those dots, and what is more, when we summarize all these pictures, and we will get exactly the same answer for domain, for range, for that one sentence, and for x-intercept, and for y-intercept. Yes? Do you want me to do you want to put that together now? Yes?
Yeah, sure.
Let's do it. Since we have covered so much, right? So let's do it. Let's do it. One sentence. Okay, I need to make this thing a little bit smaller in order to manage this properly, okay? So I'm going to insert 2 more columns. 2 more columns. 2 more columns. Okay, so one would be for 3 to the power x. And the other one would be for 10 to the power x. Okay, 3 to the power x was not in the table. 10 to the power x was in the table. Okay, and their graph. Okay, their function. So that's the rule, right? These are the rules. So this is going to be base 3 and base 3. And that's going to be base 10. These are the functions, we call them, they're in the same family. Sometimes we call it a family of curves, right, with different bases. They are in the same family, okay? So I'm going to put the curve here. Okay, so 3 to the power x. I'm going to put that curve here, and just make that adjustment. I want you guys to reflect on these features. Okay, so this is 3 to the power x, right? And 10 to the power x, I'm going to use, I'm just copy and paste this picture and then go in there, change the base. Okay, change the base to 10. So all these pictures, they look very similar. Just one is steeper than the other, or one is, wider than the other, however you name it. And their domain range, x-intercept, y-intercept, are exactly the same. So 3 to the power x, 10 to the power x. Can we make the table? Can we continue to make the table for base 100? Can we do that? It will go on forever, right?
We can categorize them under exponential function family.
Right. So that exponential family is called what? That exponential family is we have a name for it. You guys have seen this before. Okay, so 10 to the power x. So we can keep this going on and on forever. So that family is called b to the power of x, with b larger than 0, not equals to 1. That's the family. Okay, if we put all the pictures together, we see the relative positions, and we know what make the difference, right? The base makes a big difference. But otherwise, their patterns have similar patterns. If you study biology, you probably use 2 to the power x. If you study finance, you probably use e to the power x a lot.
So Professor, we can say exponential families are increasing functions.
For base larger than 1, they are increasing. But what if the base is between 0 and 1? Because you look at these bases, right? This base is larger than 1. 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 Okay, very good observation. Because when you talk about base, right? When base b is larger than 1, yes, all of them are increasing. All of them are increasing. But what if for base between 0 and 1? In fact, you will encounter a function in calculus, e to the power of negative x. Remember seeing this function, Farouz?
Yes, and
What about
yes,
it?
yes. I mean,
Is this
we
function
can,
still increasing?
if I graph it, I visually can respond, but I guess we passed the class time. I don't know if you wanna.
No, we still have time.
Do we have time? Okay.
Our class until 10:05.
Oh my God, sorry about that. I'm
No
sorry.
worries. 10:05.
Yes, Thursdays. Okay.
All right. So you see, we see it's increasing for all of these functions because the base are larger than 1. What if the base is between 0 and 1? Okay, so this is a function you're going to see as well in your calculus class. Let's roll up our sleeve to do it now. How about that? Are you ready?
Yep.
Wonderful. So we're going to do e to the power negative x, right? This is certainly is not in our table because that, but because of that wonderful question we got from Farouz, right? We're going to do it now. Okay, this was a plan for later, but since we've done so much work, so we may just as well to utilize what we have done. Okay, so this with the change of rule, okay, I'm going to copy and paste this table because I just want to take a little shortcut with the change of rule. Okay, with the change of rule, and this time the function is what? The function is what? The function is f of x equals to e to the power of negative x. But why is that related to the base b? Because e to the power negative x becomes what? It's really e to the power negative 1 parentheses to the power of x. So the base is 1 over e to the power of x. Do you follow me?
Yes.
Does everybody follow me?
Yes.
All right. So with this new rule, for the same input, okay, I need to make some adjustment because it says negative x. So when my input is negative 3, okay, my input is negative 3, it's going to be equal to e to the power of negative 3. Do you see that? Do you see that?
Yes, yes.
When x is negative 3, using this rule, okay, I'm going to use this rule everywhere. Okay, when x is negative 3 as the input, the output would be produced by replacing x by negative 3. As a result, you're going to get e to the power what? Positive 3. Do you see that? So instead of 1 over e to the power 3, you're going to get e to the power 3. Sorry. Are you guys doing it? Yes?
Mhm.
All right. For negative 2 as the input with the new rule, what will happen? This is a negative 2, and x will be replaced by negative 2. And negative of negative 2 is positive 2, that's e squared. Yeah, do you guys follow me?
Mhm.
Yes.
When input is negative 1, what will happen? This is going to be, so I'm going to do all of these. Okay, hold on. Just clean up. I'm just going to clean up. Okay, so this is the new rule. Okay, this is a new rule. I want you guys to plug in the numbers now. Do it, please. You're going to love this. Okay, and I can see you're going to benefit this tremendously. Okay, this is the power of just do it. Okay, this is the power of just do it. Whenever I see this, I always think about, someone was shooting the the basketball hoops, one after another for tens of thousands of times and becomes a master of it. But you do math, you don't need to shoot that many times. You don't. You get it much sooner. Okay. When the input is -1, so this will be negative or -1, right? And so this is end up to be what? E.
Cursor line 1 with -100 input, did you modify that or?
We
you
haven't done that
kept-
yet. We haven't done that yet.
Okay.
Thank you. We're going to get to it, okay? Especially when Farouz asking for it. I appreciate he's here. Okay, so when e to the power of -100, so this is going to be negative or -100, so this is going to turn into e to the power 100. And this is going to make a huge difference. All right, so we're not done yet. Could you guys finish the rest of it?
Now I can visualize the graph. It is decreasing. I can answer your question now.
And you got it. I didn't tell you, did I?
You helped me to build up, build up my confidence level as a student.
Thank you. Don't we see ever so clearly with these little work, these easy to do and not easy and easy not to do work? Don't we?
So the amount of time you spend and be patient, that is exactly the time we need to grasp it and digest it and understand it and think about it and all those things.
Yeah.
Again, that's why it makes the name of this class pre-calculus. We do not have time to think about all these things at calculus. So this is just the name makes sense, the name of this class, pre-calculus.
Thank you for that comment, right? We must be patient with ourselves. Okay, that's a way we love ourselves, right? Remember, I was sharing with you my younger years. I always want to prove I was smart, but I still haven't proved I'm smart because I'm just as smart as I can be. But what the saving grace is my patience and hard work. Okay, my IQ test is never going to be higher than whatever it should be. I never dare to take one. I was so intimidated to take one because I don't want to be ashamed of the possible result. But I compensated by doing what? Patience and hard work. Okay, so with patience, we obtain all things, whatever that literature is or scripture, right? So now, if you compare with the picture, we compare with the other table. Okay, I'm going to bring these two tables in comparison. Is everybody doing this? I assume everybody is doing this, right? So which table do you think we want to compare with? This table, isn't it? Yeah. We
That's a
set them
good one.
side by side. What do you see? For the same inputs, these outputs are getting smaller and smaller. And these outputs are getting larger and larger. Do you see that? Does everybody see that? Farouz said he already has a picture in his mind. Okay, but I want him to hold it just a little bit. How about everybody else? Do you already have a picture in your mind? You know, this is my favorite cup. Keep calm and carry on. Okay. It's something I see. I want to go by that. Would it be flipped by the y-axis? Exactly, Wilbur. You got it. Shall we plot the points? If we are to plot the points, what do we see? Okay, so for just make sure everybody will see this, and we have 7 minutes left, I'm going to take the curve of e to the power x. I'm going to take the curve of e to the power x, and I'm going to bring it up here. Okay, this is e to the power x. Okay, we're going to plot some points over here. I'm going to, of course, we're going to use a different color. Okay, and you see 0, 1 is still there, right? Zero, 1 is still there. 0, 1. So if I use green color, it's going to overlap with my red, because the red is a stronger color, so we won't be able to see it, right? But it's okay. So what else point you want to plot? Wait, I put it in the wrong place, sorry. My bad. Here. Okay, this is e to the power negative x, right? Do you guys follow me? Yeah, do you guys follow me? So this is the e to the power x. And we're going to plot points for e to the power negative x. I know some of you already got it. But let us be patient with our classmates and with everybody, and to see for ourselves and plot for ourselves. Okay, so I got for -1. I'm just going to plot a few points, guys. You know, you don't have to do all of them. It'd be great if you do, but we're running out of time, right? So I'm going to use green. Where did it end up to be? Excuse me. Hello, where are you? Hello.
I'm here.
You see, sometimes when I'm in a hurry, I tend to make mistakes. Oh, I need to choose a dot. Duh. You see that dot? For the same input, e to the power x lands you here, e to the power negative x lands you here, right? 0, 1, we don't need to plot because it's not going to see much of it. And let's look at 1, e to the power -1. Where is that? Right? And what else? Two with the green dots, right? It gets even lower. Do we start to have a glimpse of it? -1. Do we? Everybody? Are you proud of yourself? You're doing this? -2 as input. You should be very proud of yourself. You're doing this work. Okay, and this lays the foundation. Do we have the picture already? Yeah? E to the power -x. Make it green. Do you like green? I like green. Is it increasing or decreasing? The answer is obvious, right? The answer is obvious. So exponential function is not always increasing. Decreasing. Then how about 2 to the power negative x? We just did e to the power negative x, right? How about 2 to the power negative x? 3 to the power negative x. Can you do them all? Of course you can. But we're not going to do it in class. We don't have that kind of time. All right?
So, Professor, do we call also these functions exponential functions?
They're all exponential. They're all exponential. All of these are exponential, right? For example, this one is exponential because the base is 1 over e to the power of x. And this one is the base is half to the power x. And 3 to the power negative x is really 1/3 is the base. You guys see that? 1/3 is the base, and so on and so forth. So all of these bases, remember the family of the family is defined as b larger than 0, not equals to 1. They're all fitting in that category. So now we're going to add some more stuff to our summary. So they are still in this family. We're still in this family. But what do we see here is that when the base is larger than 1, b to the power x is what?
Increasing.
Increasing. In this family, it increases. Increasing function. How about b is less than 1? Between 0 and 1, because b has to be positive. Okay, b has to be positive. Instead of increasing, it's decreasing. Okay, I think that concludes today's lecture. And I'm extremely proud of you because you guys are so patient with yourself. You did the work, and I guarantee you that this work will build a foundation, and in the future, we will quote them. We will quote them. Not only I will be quoting them in this class, in your future classes, they will be quoted, especially e to the power x and e to the power negative x. So finally, if I can take a little bit more time of a little bit more of your time, and I want to add another piece of summary into the picture. Shall we?
I say yes.
Thank you. Thank you for your enthusiasm. Okay, so I'm going to add, for the practical purposes of your taking the calculus class, right? So I'm going to bring this one on the very top. So what I'm going to insert is I'm going to insert this column. Okay, and this column I'm going to insert is going to be this guy. E to the power negative x. Very useful function. I promise you, you're going to get to use it. And I'm going to put the picture right there. Put this picture, okay? It's a wrong picture, but I'm going to make changes, okay? So this is going to be changed to be e to the power negative x. We already grabbed that function, so that's not a problem, right? This is e to the power negative x. How about domain range stuff? Everything the same. E to the power negative x is going to be forever positive. Same y-intercept. In your future classes, you might encounter these. Sometimes you might see e to the power 2x. I'm sure you can handle it. There will be a lot of variations of this e function. But in most of the situation, in the future classes, in your calculus classes, you will see e to the power x and their variations a lot. Okay, I think that will conclude today's lecture. And do you want me to send you this table?
Yes.
Okay, so I will do.
Yes.
Yes, please.
I will send you this table, but mainly I want you guys to really dive into the details so that you will never forget. You never forget, because after you've done these detailed work, we're not even shooting 1,000 loops, right? You already got it. You already got it. So we just want to reinforce it. So it's gonna take a little bit of time to make sure the typesetting works right, because I want to guarantee that the PDF file will work properly. So I may have to break up the table, or whatever I'm thinking about at the time, but I will send it to you as soon as possible. And this week, yes, go for it.
No, I just want to say thank you, Professor, but go ahead.
Yes, today's Thursday. I will see you guys on Monday, but please do expect another quiz. And the other thing is, as I mentioned at the beginning of the class, that quiz number 3 grades has been adjusted. And if you have any questions, please don't hesitate to contact me. Okay, so I will see you guys on Monday.
Wait, I have
Thank you very much, Professor.
All right,
Great
thank
job,
you.
you guys. Great
Wait, I have
job.
one quick question.
Yes.
So my first question is, when we do the homework, what are the answer keys to check if we did it correctly?
That's a very good question. Okay, that's a very good question. I actually meant to address it. Thank you for reminding me. I actually don't have the answer key for you. And the reason I'm not going to give you the answer key, then you say, how do I know if I'm right or wrong? And use me as a resource, and I'll always be happy to confirm or not. But my real goal is to make you yourself to be the ultimate judge of your work. And I'm showing you the way. The 6 principles are all there. As someone who teach mathematics like me, those 6 principles are my principles to judge your work. And these definitions are these principles I judge your work. And I want to tell you, when I was a student, okay, at the beginning as a student, all those many years ago, at the beginning, just like you do a problem, you check the answer in the back, you do a problem, you check the answer in the back. If you don't get the right answer, you do it over. This is not good enough. In particular, sometimes you always have those even number of questions that the answer is not given. So you have to rely on your own judgment. And for me, as a philosophy, I want to help you guys to become more self-sufficient. It's going to be a little bit difficult. There's going to be a little transition. Okay, there's going to be a little transition, but you can make it. So ultimately, you will be able to judge if your work is right or wrong without having to rely on that crutches, which is in the back of the book. So this is the reason why I'm not going to give you the answer. However, you can always rely on me as your resources, asking questions and send me a picture, say, oh, did I do this right? And I will get to it as soon as I can. Would that be an answer satisfying you?
Yeah, but
and I promise you, in time, you will be better and better yet.
Okay. I guess another question is, would you mind going over like 2 questions in the homework for class, or would that not be okay?
Of course, I would love to. Okay, it's just gonna keep you guys a little bit longer.
Okay.
Yeah. So what is it?
Sorry.
Go ahead. I'm delighted you're asking questions. Is this a basic what?
It was basic 21.
Basic 21. Which one?
Do you pull up the notes because the way it was written out was kind of weird.
Okay, I understand. Which row, which column? Or should I bring this up? Let me bring this up to help you to identify that question. Or you can take a picture and send it to me. Okay, I'm trying to find that page.
Do you think you can go over row 7, column C?
1, 2, 3, 4, 5, 6, 7. Row 7, column C.
Yeah, it should say like pi over 1 plus e over 0.
Oh, pi over
1 plus e.
1 plus e to the power 0.
Yeah, because I don't know if I got it correct, but I just
Okay. In order to identify the answer for this one, all you have to decide, because we have a 0 power, right? And we have that principle, b to the power 0 is equals to 1, provided b is not what? B is not 0. And the base here is the entire parentheses, and the entire parentheses in which is the base is not a 0 for sure. We know the value of pi, we know the value of e, therefore the answer is 1. Next. You got it?
yeah.
This is applying that. Next.
Can we do one from 22?
Of course. Do one on a basic 22? Of course. Which one? Your pick.
Can we do number 14?
Sure. 22, number 14. 22, right? I'm sorry, 14.
Yeah. You want me to read it to you?
No, I got it. 2 to the power negative 1 multiply 3 to the power negative 1 and then to the power of negative 2, right? Is that right?
Mm-hmm.
I'm making the fonts a bit larger. Okay. You know, recall the principles we reviewed. Okay, I'm going to scroll down real quick to bring up those properties we reviewed. Okay, like b to the power of stuff. It's hard to find. So let's just forget it. I'm just going to type it over. Okay, no problem. So we have seen that if we look at to review the material, we know that b, you know, a to the power of, let's see which property applies here. Okay, so a times b raised to the power of something, right? That's equals to a to the power of n times b to the power of n, right?
Yeah.
So our capital A is 2 to the power negative 1. Our capital B is 3 to the power negative 1. So as a result, okay, so what do we have next is we're going to have, this is a capital A raised to the power of negative 2. I'll show you another way to do it, okay? And the next is 3 to the power negative 1. And then to the power negative 2. Okay, and then we have this property here, b to the power m then parentheses to the power of n sorry, wrong typing, to the power of n equals to b to the, what I'm doing here, sorry, equals to b raised to the power of m times n. Yes, do we know this property? Yes?
Mhm.
No? Okay, and then for this one, the base is 2, right? And the power. So one is inside and the other one is outside the parentheses. So we're gonna multiply these two powers, which is a -1 times -2. And the other one can be done similarly. Do you see that?
Yeah.
So in the end, we get equals to 2 to the power 2 multiply 3 to the power 2. And in the end, we get 4 times 9 equals to 36. Another way to do it, okay, another way to do it, you can do it another way. It's a bit, okay, there's another property we learned is that b to the power of -n is equal to what?
1 over b and
b to the power of n, right? Okay, so you can use that. If you use that, what you can do is that you can rewrite the whole thing, and 2 to the power of -1 will be 1/2, isn't it?
yeah,
3 to the power of -1 will be
1/3.
1/3, right? And then you take care of the inside the parentheses first, and you will have inside the parentheses 1/6, and then to the power of -2, right?
Yeah.
And then you can use this property or you can use that property, capital A, capital B, raised to the power of n equals to a to the power of n over b to the power of n. Yes?
Yeah.
Okay, so you can do either way. If you do this formula, okay, if you do that formula, you can get 1 to the power of -2, and here is going to be 6 to the power of -2, right? Yes?
Yeah.
And then uses this property again. Okay. 6 to the power -2 will flip up. So you get 6 to the power 2, right? 1 to the power -2 is just 1, so it's flipped down. So in the end, you get 36. Does everybody follow me?
Yeah. Okay.
Right, so basically using the power properties.
Okay.
Since you
So-
ask, I'm gonna do another one for you if you wish.
I was gonna say it was okay to do another one, so I guess that works out.
I love it. I love it. So which one? Maybe we do one for on the other side, right? On the other column, right?
Okay.
Take the first one. How about that? I can do one more for you, no problem. Yeah.
Okay.
To the power -1. In this case, we cannot apply the negative sign, the negative exponent to the inside. We cannot. You follow me?
Yeah.
Because all the properties we learn is about multiplication and division. Okay, for example, b to the power of m multiply b to the power of n. If you have those property in front of you, or you find any elementary algebra textbook and you're going to find these properties, you will notice that they only apply to multiplication or division. So there's no such properties that you cannot apply this negative exponent inside. So what you have to do in this case is that you're going to have to do this. And this is going to be turned into 1/2. And that's going to turn into 1/3. Got it?
Yeah, and then you would have to do on the left side times 3 and the other side times
You're
2.
going to have to do the common denominator,
Yeah.
which is going to be 3/6 plus 2/6. Okay, remember at the beginning of the semester, I was telling you this class is 5 courses in one. And this is the contents of pre-algebra. I pick out these exercises from a pre-algebra textbook, which turn out to be very useful for all of our students. And in the end, you're going to get 6/5.
Okay.
So the column on the left, we cannot apply much of the property of exponents. The column on the right, we can apply those properties.
Okay.
Anything more you wish me to do?
No, that's really it. Because I was doing it right, and I realized I was I was doing it right, but I did it like a different way, and then I started to realize, wait, this doesn't make sense. So I kind of like redid it over and did it over a different way, and I wanted to see if I got the answers were correct or not.
Good. Anytime.
Okay.
Anytime. Yeah.
So yeah,
Okay.
that's really it. Thank you so much. I guess another question would be, do we have homework today or for Monday?
Yes, you will have homework today.
Okay.
Okay, I'm just going to have to contemplate it and put it together for you.
All right.
And do expect another quiz. Remember, I do have another quiz for you.
Yeah. All right. Thank you so much.
All right, great job. I'm so glad you guys are doing homework. And I'm looking forward to seeing you guys on Monday.
I'll see you on Monday. Thank you.
Bye. Any questions, Nicole? And Brendan's there? No question? Okay, I'm going to stop the recording.